Now, one of the immediate consequences of this is that if you have an abelian group, then all its irreducible representations will have to be one dimensional, because if it is an abelian group, then this condition is always satisfied. You can always find a T which will you can convert a sort of a corollary. This can be seen from this preceding statement, because take a specific element H and take its representation. Because the group is abelian, TH will commute with any T of G. For all G. That means T of G has to be proportional to identity up to a constant. But I can play this game with every single element H of the group G. Repeating this for every H belonging to G, we see that all elements of G are proportional to identity, which is then the identity matrix, whatever size it is, n by n is irrelevant. It's essentially the numbers that are representing those elements. The irrep is one dimensional. So that is one nice result that immediately follows. In case of physics, we also know that there are symmetries of the Hamiltonian. In quantum mechanics, if Hamiltonian H has symmetry group G, then the representation on any representation of irrep of G, H has common eigenvalues. This is because H Tg equal to Tgh, because H has to commute with elements of G. The G is a symmetry of H, so H has to commute with T elements. So this means that H must be proportional to some lambda times identity over that whole multiplet. So this we usually call these degenerate multiplets. So those are sort of the immediate consequences of Schur's lemma. Okay, so much for Schur's lemma. We next wanted to prove the great orthogonality theorem. Actually, the proof is not very long. And although it is also technical, it is somewhat less of abstraction. It is a constructive proof, like the proof we had about finding a unitary representation. So let me see if I can attempt this, because we do want to finish off the formal parts. So this proof of got or what is quite nice, and it is similar in nature to that existence of unitary representation for every existence of finite dimensional unitary representations. So let me call this the wonderful orthogonality theorem. Also known as great orthogonality theorem. Dresselhaus's book, the one that I said I have given link today, it ascribes this to a mathematician called Van Vleck. So I don't know, you can call it what you like. Some people just call it the orthogonality theorem. Then it becomes taught, I guess. Okay. So in here we want to show that we want to show a result of this type. Given irreps d alpha and d beta, now watch carefully what we are writing. D alpha I L G d beta M J G inverse is equal to, so you take matrices from representation alpha, and on the right you multiply by matrices from representation beta, some other representation, and then sum over all G. Note that here the sizes of D don't matter, because I have kept, in fact, all the I, L, M, J are not summed over. So So I take a particular representation and I take another representation. I pick any one element IL from one of them and Mj from the other, but now I sum over all the group elements. So the summation is only over G. The claim is that this will result in a bunch of deltas, Kronecker deltas, delta Ij, so all G belonging to G. This is equal to delta Ij, delta ML and delta alpha beta times, so there is some normalization, order of G divided by n alpha, where n alpha is the size of the representation. Okay, and G is order of G, the size of, that group, order of the group G. So this is the orthogonality theorem, that if you take representation matrices from two different representations, you are going to get 0 effectively. If you sum over and you pick some specific elements and you sum over all G, you will just get 0, unless alpha is same as beta. So there is a delta alpha beta, unless the representations are the same, and in that case you are forced to choose I equal to j, this index equal to that index, and if L is equal to m, I what have I written, I L and m j, I j m L, this is correct, yes. So so I equal to j and m equal to L, only then I will get a non-zero answer, and that answer will be equal to the order of G divided by the size of the representation. So it is some kind of an orthogonality relation. Only if various things coincide, then the vector magnitude of the vector turns out to be this mod G over n alpha. Otherwise it is all those things, treating it as a, so this essentially treats these elements of the representation to be vectors of size G, the order of G, because this summation runs over G means that if you think of this as an inner product, then we are, the number of components, the number of components is equal to the order of G. Okay. So to prove this, one takes a clever construction. So we take any arbitrary x we like. Just take any such x and then construct A equal to sum over G, let me write it first, d alpha, and I will stick to this notation, d alpha G and capital X d beta x inverse, and sum over all x belonging to G. So, we have so far not used x for elements of G, but we will just call it x. So, the sum is over G, and since x is this alpha to beta kind of map, it can act on alpha beta size matrices. So, this is a rectangular matrix which links on this side to beta representation, this side to alpha representation, but now we sum over all G and construct such an A. Now what we will do is cleverly use Schur's lemma, using this as the A that commutes with alpha and beta. So now consider hitting such an A with d alpha G. This means I take this d alpha G and bring it under these right inside the summation, and that is why we had kept this summation index x. And now just look at the expression for A, which I am reproducing here now. But now, and I have d beta of x inverse. Now I multiply the right hand side by d beta G inverse d beta G. This is identity, right? It is just taking G inverse product, and I apply it to this side. So, G is a constant, it is some specific element where x is what is being summed over. So, if I hit by d alpha G on the left, I can take this inside this summation, but additionally from the right hand side I hit by d beta G inverse d beta G, where G is the same. Now you can see what has happened. So, now d alpha G d alpha x, because d is a representation, it has to convert it into d alpha of gx, and d beta x inverse times d beta G inverse has to produce d beta of x inverse G inverse, which is same as d beta of Gx inverse, right. And now we can think of the summation to be over G times x. And we are left with this trailing d beta G. But this is nothing but this summation is nothing but our good old A. It's just that we have shifted the summation by multiplication by a G, and I think this is where they invoke this so called rearrangement theorem. It's essentially like having rearranged all the G elements in another order. So this is same as A times d beta G. So you see what has been done. D alpha G on A has been converted into A times d beta G. So we can apply Schur's lemma to this A. Okay. And I suspect that this is why it is called lemma, because it was being used in this theorem, although by itself it looks quite a powerful theorem. So now by Schur's lemma, A would have to be 0 unless alpha is equal to beta, and if A is if alpha is equal to beta, then it would be proportional to identity. So we can write this statement as this has to be firstly proportional to delta alpha beta, because otherwise it will be 0. I mean, so if alpha is not same as beta, it has to be 0, and if it is non-zero, then it has to be proportional to some lambda times identity matrix, and this lambda may depend on the choice of x. What x is will decide what this lambda is, other than it is identity. And most often I write this, it's called blackboard style or something, this script 1 with size of the matrix, but right now size of the matrix is okay, so it's like dim alpha or something like that. So it's alpha by alpha. Anyway, you understand what this means. Now what we do is that we choose x such that its only non-zero element is LM. So firstly we have already established alpha is equal to beta, so all these are now square matrices, and in that representation in that size matrix in X, set everything to 0 except one particular element LM. So that will mean that I can now drop this X and just replace. So, I write out the matrix multiplication explicitly, but this as only non-zero at L and M. So, this implies that sum over all G belonging to G. Now, d alpha of G, and I take some I, but X allows me to have only non-zero L element, and then d beta, well, this is also going to be alpha, but okay, d beta of M and J G would then be equal to this undetermined lambda x times delta alpha beta, and because this is identity matrix, it means that it has to set I equal to J. Finally, we need to determine this lambda x. So, to do that, firstly of course, we use alpha equal to beta. Use the fact that alpha is equal to beta and sum over trace over ij. Then on the right hand side, I simply get lambda x times n alpha. So, I basically get summation over this Kronecker delta, whose size is the size of the representation alpha. So, n alpha is the number of diagonal elements in the identity matrix, that is equal to size of the representation. Whereas on the left hand side, we get sum over G d alpha I L G, and we have agreed now to take the same representation. So, and M, and now I am setting I equal to J. So, there is summation over this I as well. But this is same as, so far I wrote these out as these are just entries of the matrices. But once I am doing a sum, I may as well bring these numbers to the left of this, because it is a row column, it is a matrix multiplication. So, I am getting basically the Lm element of G inverse G. But G inverse G is the identity. So, this is just, it will be represented by identity matrix. So, it will be proportional to delta ML, and the summation over G will just give me size of the group G. What it says is sum over all the G, or that is sum you have as many terms as there are elements in G, but each term is just the identity matrix. So, it is just counting the number of elements in G. This summation has collapsed because this is just equal to, if you want, it is equal to sum over G d alpha of the identity E. But you have to do this for every G, you have to count this for every G. So, that produces G. So, let me put it in quote marks, this is what it boils down to. So, it just counts the size of G and M has to be equal to L, otherwise this will be 0 because this is representing the identity matrix. So we got this on this side, and that ends the theorem, because now we put together these left hand side and right hand side. You can see it right. Equal to nx times lambda x times n alpha, or lambda x is equal to so putting it back, and that is the got, what, or tot, whatever you want to call it. G inverse. But we quickly can improve on it a little bit by observing that we will always be using unitary representations. So G inverse will be same as G star. So for unitary reps, this becomes equal to so then it becomes just summation over G. Except that I have to change the order. From mj, I have to write jm, because u dagger equal to u inverse. So I will use unitary rep and use it in this form. That is why I made the mistake of not putting G inverse there. So then it actually becomes much nicer. It's just summation over G. No, you don't have to refer to the G inverses. Sum over all G. This is the orthogonality theorem. Okay. So this will be used to prove things such as the number of irreducible representation is same as the number of independent conjugacy classes. You can imagine the conjugacy classes in a group is finite. There are only so many conjugacy classes. And now we will be able to check that the number of irreducible representations can't be more than that. It is exactly same as that. So that list of irreps stops. It's also finite. And that is how character tables are usually represented. Just row and columns are just irrep versus classes. Okay, so we'll stop here today.